All right. Greetings to you. I welcome you to the conversation we have in, math for economics, and I want us to continue with the conversation. Now we look at constrained optimization. I do understand and realize that in the previous conversation, what we had was unconstrained optimization, where we were trying to make mention to us that under unconstrained optimization, the objective function is maximize or minimize without a limit, right? There is no limitation whatsoever. But this time around, when you come to constrained optimization, the conversation is a little bit different. We have a limitation, we have a constraint, we are constrained. So how do you handle constrained optimization? That's the message that we are sending across. There is always a constraint here. Now, economists like you, deal with the allocation of the scarce resources among alternative uses. The concept of the constraints and these restrictions is therefore important. There are two approaches that are used in solving, constrained optimal problems, and these substitution method and the Lagrange multiplier, Lagrange multiplier, and substitution method. Right. Let's use substitution method and let's have the example. Now, listen carefully. The question is reading, and I read in your hearing. Consider a firm producing commodity Y with the following production function, and the production function is 5x1 and x2. Without any constraints, the firm can produce unlimited, quantity by utilizing unlimited amount of x1 and x2. That's what can actually happen. That is if we don't have any constraint, right? When you optimize this function, it's a production function. So it means that the firm can produce whatever number of, outputs, and the output at that point refers to x and y, right? They can keep on producing as much as they want because there is no limit. But when we come to constraint optimization, the conversation changes a little bit. Now we have a constraint, right? We have our own budget constraint, and our budget constraint is we know that the original function that we had was 5x1 and x2. That's what we have. This is the objective function, or the function that we're trying to, optimize. Now, it is subject to a constraint. The constraint that we have is we assume the maximum amount of the money that you have is just 100 for the two inputs, x and y. So you know that now you are limited. Your income is now limiting you. The maximum you have is just 100. So you're just making sure that you can spend just 100 on the inputs. And these inputs that you want to buy so that you can use them in production are priced different. For example, the first unit, price of X, unit X, you input X is 2 kwacha per unit, and then, input 2, that is X2, this one is 1 kwacha per unit, okay? And the total is 100. So the constraint, therefore, our total budget shall be, we know that the units of X plus the units of X1 and X2 that you produce, consolidated together, they should give you 100. So how much of the X are you producing? X1, the price is 2 kwacha per unit. This X is the number of units. So if you want to know how much you have spent on X, it shall be 2, which is the price per unit, multiplied by X, which is the number of units for input X. Then when you go to Y as well, it's how many per price is just 1 kwacha multiplied by the number of units for price 2, which is just X2. When you consolidate these together, your budget should fit your 100 kwacha. They should be equal to 100 kwacha. And therefore, this is your, your budget constraint, right? So the generic formula, I just want to give you the general formula for the budget constraint. The budget constraint shall always price of good X times the quantity of good X plus the price of good Y times the quantity of good Y. They should be equal to the budget, the total income that you have, M. This is the general formula that I introduced to you. So for that, we insert the price of X1, which is 2, X1 plus C. We don't have Y. Instead, we have X2. So price of X2 is basically 1 multiplied by, quantity of X2 is just the X2 like that, equal to the income of 100. We can summarize this as 2X1 plus the X2, all that equal to 100. So at this point, we have dealt with the constraint. We have known what the constraint is. But now we are maximizing the function. The function that we have is, what's the function? Is 5x1, x2. We want to maximize this function subject to this constraint. How is it set? All right. We're using substitution method. Now, substitution method says the following. It says that what you could do, number one, you can go to the constraint, your constraints 2x1 plus x2 in our case, equal to 100, and make substitution effect is about making one input subject of the formula, right? Make one of the inputs the subject of the formula. If you happen to make x2 the subject of the formula, we shall have 100 less 2x1. So wherever there is, listen, wherever there is in the function that we have 5x1, x2, everywhere we find x2, you shall substitute by putting this particular function 100 minus 2x, so that it can be 5x1 multiplied by 100 minus 2x1, like that. And if you do your computations, you should be able to find 500 x1, minus 5x1 times 2, negative 2, that would be 10 x2 squared. 10 x1, this is x1 squared. Yes, that's what we have. And set all that equal to 0. All right, let me just show you how that works. Okay, when that is done, you will do that. You have this function that is equal to 500 x1 minus 10 x squared. Now, with this substitution, the constraint maxima problem is actually reduced to a free maxima problem with one independent variable, in this case, which is just x1 and x2. So what are we going to do then? Then what you're going to do from here, you got to differentiate this particular function with respect to x1. We have reduced the function. This is our function. Let's call it function y. We are differentiating it with respect to x1. So that will be dy over dx1 and set the derivative equal to 0. When you differentiate that, you shall have 500, minus 20 x1, like that. That's the derivative of that. Now, you set the derivative equal to 0. That's the message you communicated. You could have the first derivative set equal to 0. And when we set this equal to 0, you shall have 500 equal to 20x1. Divide through by 20 so that you can get x1. And your x1 at that point is equal to 25. So we have found the x1. What else do we need to find? We can easily find the x2, right? If you have found x1, then x2 should be easy to find using these same functions. So using the same function, we do know that at that point, we have found the first function, Let me just get back a little bit. you have seen the value of x1 is that. Then you go back to the constraint. Our constraint was 2x1 plus x2 equal to what? 100. You can substitute x1 now into this function. You have 2 times 25 plus x2 equal to 100. So that this can give you 50. 50 plus x2. We want so you've actually found the values of the what's this? The critical values using the first derivative x1 and x2. But the issue is that you don't know whether this function is a maximum or a minimum at these points, right? You don't know it. You don't know whether the function is a maximum or a minimum at point at the x1, which is equal to 25, and also at x2, which is equal to 50. We don't know. So for us to test whether the function is a maximum or minimum, we say at that point, we need to do the second derivatives. We need to take the second derivatives. Of this first derivative now, let's do the second derivative. Differentiating this for the second time with respect to x1, you just have negative 20. And negative 20, if you look at it, is less than 0. The derivative, the second derivative is negative at that point, less than 0. And we said that if the second derivative is less than 0, then the function is what? It's maximum. If it's negative, the second derivative is negative, then you have a maximum. All right. So if the x1 is 25, then we know that to find the x2, then x2 is just what? It's just 50. Now, we do know this is a very simple case. It's a very, very simple case when you're dealing with this all the times. Why? Because sometimes the constraint that we can give you may be very complicated, as a substitution may not work. So at that point, we need another method. This is where we employ what we call the Lagrange multiplier. The Lagrange multiplier comes in when the substitution effect, the substitution method fails, or when the substitution method really does not give us what we want, then we can go ahead and employ the Lagrange multiplier. Now, the Lagrange multiplier is about us introducing another variable. The Lagrange, a mathematician, formed what we call the augmented function. Now, the augmented function at that point, this is a function trying to combine together the constraint and the objective function, put them together as one. And then they introduce another variable, and at that point, a new variable they introduce, they call it lambda. This is the value, lambda, right? This is the lambda. Now, this lambda is basically what you call the Lagrange multiplier. It's the Lagrange multiplier. So we have the augmented function, which is now this function, combining together the function, the objective function. So the formula is, right? The objective function with respect to the variables, plus the augmented, the Lagrange, multiplier, that's the lambda in our case, multiplied by the other function, which is basically the constraint. So the constraint reversed, the inverse of the constraint gives us x1 and x2, like, in terms of x1 and x2. So that's what we do. That's the formula. So in our case, you saw that the objective function actually was 5x1 and x2, right? Plus the Lagrange multiplier, open, you invert the subject versus the constraint, which was 2x1 plus x2 equals to what? To m. What you could do, actually, you could easily invert this. And when you invert this, it can still be m minus 2x1 minus x2. Basically, you have made these variables cross the equal sign to the other side of the equation, and then you are good. So it's one way of stating the Lagrange problem. This is how you're setting, right? It's one way of setting up this augmented function. Or the other way, you could set it up like this: 5x1, x2. Then if you put negative here, negative lambda, what you do this side now, you will not invert the function. Only the m will cross the equal sign to the other side. X1 plus x2 equals to m, which is the constant, the 100, your 100 yes, your budget. If your m be the one crossing the equal sign, this will become just negative m, like that. So your function will be 2x1 plus x2 minus 100. That is if the 100 is the one crossing to the other side. But if these are the ones that have crossed the other side, then the specification will be the one on top. But if you do the opposite, then the specification will be this down one for the augmented function. And so this is the augmented function for you, and you should be fine with it. So this is the augmented function, right? Okay. Now, when you set up the augmented function, what you do now, then you do the partial derivatives, right? You're going to do the partial derivatives. To do the first derivatives with respect, the first partials with respect to x1, with respect to x2, and with respect to lambda, and set all of them equal to 0. Then solve them simultaneously to find the critical values. That's how that is done. I repeat, when you set up the Lagrange like this, the augmented function, all right, it is equal to the end up of x1 and x2, plus lambda, open the bracket, your m minus 2 minus whatever, maybe x1 plus the x2, whatever it is, right? Then you have to do the partials on this. The first partial, the partial from that with respect to x1 means you're differentiating this entire function with respect to x1 and set it equal to then again you do the second the first partial with respect to x2, all right, on the same function. Then you do the third partial now with respect to z. For us, this one, the inverse of the 1 plus c, x2 to the other side. So you have 100 minus 2x1 minus x2. So that's what you put here inside the brackets and the Lagrange, right? Then what you do from here, you can easily FOIL so that you understand your 5x1, 5x2, lambda times 100, you have plus 100 lambda minus 2x1 lambda minus x2 lambda. Everything is equal to 0. Then we start now doing the partials. Let's call this is the augmented function for us. We're differentiating the augmented function and doing the first partials with respect to x1, right? The x1. Let's differentiate it with respect to x1. So the first function it will give you 5x2 because x1 is disappearing. From what you learned on how you differentiate the partial derivatives, And where else do we have x1 here? X1 is disappearing, then you have minus 2 lambda, like that, equal to 0. These ones which do not have lambda shall be just set as zeros. They'll become zeros, treated as constants. Then again, when we come to do the second partials with respect to x2, you will just have this x2 is disappearing, then you have 5x1. Where else we have x2 is here, we have x minus x2 and lambda, so it will just be minus c lambda because x2 is disappearing, set equal to 0. And the next one, we are differentiating with respect to lambda, the last one. So we know that here we have 100 lambda. 100 lambda. Lambda is going because it just raised to the power 1. You remain with 100 minus c 2x1 because lambda is to the power 1 there minus c x2, which is basically the same objective function you're saying. This is the same constraint and set it equal to 0. Then you will have to solve for the unknowns, right? For x1, x2, and lambda. That's what we're doing. Okay. So when you do that, then you have these functions that I'm talking about. And then you are solving for x1, x2, and also for lambda. Let's solve them. We are solving these 3 equations simultaneously. You know how to deal with the simultaneous equations, right? Your equations are 5x2 minus 2 lambda minus 2 lambda is equal to what? 0. The other one is 5x1 minus lambda is equal to 0. The other one is 100 minus 2x1 minus x2 equal to 0. We can even use substitution effects, the subject of the formula, right? So that you can have your life made easy. We want to solve for x2, basically solve for x2. How do you solve for x2? We want to solve for, can even start by solving x1. How can you solve for x1? Whichever you want to start with. The equation is 5x1 minus lambda equal to 0. So have lambda. We want to solve for x1. We'll have 5x1 is equal to lambda divided through by 5 so that the x1 is equal to what? Lambda over 5 or 1 over 5 lambda. Okay. Yeah. Then let's solve for x2. Solving for x2 as well is something that is just as good as what is as water. 5x2 equal to 2 lambda. No negative 2 lambdas cos the equal sign. Then you divide through by 5. And this is your x2. Now you have the x1 and the x2. Then we want the value of lambda. What you do, this x1 and x2 shall be substituted into this last function. The 100 minus 2x1 minus x2 equals to 0, so that we can solve for lambda. How is it done? So we shall say 100 minus 2 times x1, we say this x2 is basically 2 over 5, lambda. So we shall have 100 minus 2 lambda over 5 minus 2 lambda over 5 equal to 0. We're solving for lambda. What do we do from here? We could have 100 across the equal sign on the other side of the equation, or you can work out this first on the other side. 100, the common denominator here is 5, and then you have negative 2 lambda, negative 2 lambda, which will give us basically negative 4 lambda. So you shall have 100 minus 4 lambda over 5 equal to 0. So you want the value of lambda. What do? So 100 is crossing the equal sign to the other side, or the lambda, 4 lambda over 5 is crossing to the other side of the equation, so that we can have 100 equal to 4 over 5, lambda. And then we are solving for lambda. What do? The cross multiply at that point. No need of suffering. Cross multiply. Yeah. 5 times 100, this will give us 500 is equal to 4 lambda. Divide through by 4, divide through by 4, like that. So that lambda can be equal to what? What is 4 divided by 500? That's the value of lambda. What's the value of lambda? The value of lambda is just basically 125. Okay, 4 into 500 is basically 125. So we have found the value of lambda and the value of x1. X1, the value of lambda is 125. So if you want the exact value of x1, remember I just expressed that x1 is equal to lambda over 5, right? So you want the exact value of x1, just put lambda there, 125 divided by 5. So what is 125 divided by 5? This will be 2, remainder 2, this should be 25. So x1 is equal to 25. Like, get the value of the lambda that you find now, put there in the values of x1 and x2. For x2, it is 2 lambda over 5, and we know lambda. Our lambda is 125, so 2 times 125 divided by 5. 2 times 125 should be 250, right? That is 200 and 250. 200 is basically 50 is equal to 50. X1 is equal to 25. Then lambda, the Lagrange, is equal to 125. So these are the critical values. So it was very, very imperative that you understand constraint optimization, especially using the Lagrange. The rules are that when you're using the Lagrange multiplier, basically, number one, can you set up the function, the Lagrangian function, the augmented function, then do the partials, partial with the first variable, partial with the second variable, partial with the lambda. If you have 5, variables, you can even do partials for all of them until you finish them. Partial for this variable, partial for the other variable, partial for the other one, and then you also do the partial with respect to lambda. It's also a variable. Once you're done doing those partials, then you can express, those values of x with respect to lambda. They can be expressed as functions of lambda. And then get those functions with lambda, insert them in the constraint, or in that partial which is differentiated with respect to lambda. Put there. Then solve for lambda. When you find that lambda now, you go back to put those expressions where you put lambda there and have them, and you're done. So that's how it is done. Okay. This is a bit about the Lagrangian multiplier that you've actually been hearing about. Now economists usually like just going direct to the use of Lagrange technique over the substitution method. Why? Because the Lagrange is easier to handle for most cases, right? And it does even provide additional information, the lambda. The value of lambda actually has an economic interpretation. Yeah, it has some economic interpretation. That's why we go for it, actually. Now, we're trying to show you the other version of expressing this Lagrangian function. Again, that this is the one that I was just trying to make mention to. Basically, it's just, so when you get the Lagrange multiplier will measure the sensitivity of the augmented function to changes in the constraint. Basically, the Lagrange multiply of the Lagrange function, the augmented function, right? How sensitive is the augmented function with respect to changes in the budget constraint, in the constraint? If the constraint is changing, really, how does that really impact the entire augmented function? That's what the Lagrangian, the Lagrange measures. All right. Any questions? Can end here now.